Welcome to Lesson 7, Why Do Things Change Your Speed or Direction? Activity 7.1, Changing Speeds. So this is part 2 of Activity 7.1. And if you remember, our learning target is we will analyze, let me get rid of that outline box there. We're going to analyze 3 objects moving in different directions or different ways to determine the relationship between the forces acting on them. And in this one, the expectation for you is we're actually going to complete activity 7.1. Remember, part 1 was you filling out the table. Now we're actually going to open up our books, and we should all be on page 79, and we're going to complete the activity. Now, a little reviewing first. So let me ask you this. If an unbalanced force is applied to the left side, causing the object to start moving, in which direction does it move? So if this force right here is pushing on this object right here, in which direction do you think it's going to move? Well, you probably figured out it's going to move in that direction. Now, that should make sense that it's moving in that direction because that's the way the force is applied. How often do you push on something one way and it moves in the opposite direction? Physically, according to physics, that should not happen. So it should move in that direction. So the direction right here, the direction in which way it begins to move, should be in which way the force is applied. However, when you start applying forces in different directions and you have balanced forces, you have unbalanced forces, things can sometimes get a little confusing. Now, let me ask you this. What about situations in which the object does not speed up or slow down, but moves at a constant speed? So this is a review of what we covered in part 1. What type of forces cause things to move at a constant speed? Are they balanced forces or are they unbalanced forces? Well, what do you think? What are your thoughts? Are they balanced or are they unbalanced? Well, let's look at Newton's first law. Newton's first law of motion. An object in motion remains in motion, and an object at rest remains at rest unless acted upon by an unbalanced force. Or sometimes it'll say acted upon by a net force. So it has to be an unbalanced net force, right? Okay, so think about this. An object in motion remains in motion. An object at rest remains at rest unless acted upon by an unbalanced force. So again, what are your thoughts? So again, let's read this. An object in motion remains in motion unless acted upon by an unbalanced force. So something that's moving at a constant speed will remain at a constant speed unless it's acted upon by an unbalanced force, which means the forces are balanced when it's at a constant speed. And what about something that's not moving? Well, the law of conservation of momentum. The total momentum of any group of objects that are not subjected to external unbalanced forces is constant. So things that are in motion will remain in motion if the forces are balanced. It'll remain at, well, let me put it this way. It'll remain at a constant speed. If it's slowing down, yes, it's still in motion, but then you have unbalanced forces acting on it, because we talked about that in part 1, where it would be slowing down, speeding up. But if it's a constant speed, again, it'll remain at a constant speed unless acted upon by unbalanced forces. Now, no motion. What type of forces act on a motionless object? We just talked about that. They have to be balanced forces. So, pull out the sheet that you were working on yesterday filling out, or part 1 you might have been doing earlier today. So pull out the data table from part 1. At the bottom, they want you to talk about acceleration and deceleration. So what is the difference between acceleration and deceleration? Well, acceleration means an increase of speed. Typically, when we talk about deceleration, it means a decrease of speed. So a lot of times we say, well, I'm accelerating or I'm slowing down. We don't usually use the word deceleration. However, you got to be careful. When we talk about acceleration, if it's a positive number, does mean an increase of speed. However, in physics, acceleration could be negative. And if it's a negative number, it also means that you're decelerating, that you're getting to move slower. So acceleration, yeah, typically we think of it as an increase of speed. However, if you're looking at science-wise, if acceleration is labeled as a negative number, it means it's not increasing. It's decreasing in speed. So you got to be careful with that. So let's look at our book now. Let's read the procedures. Every airplane has at least 4 different forces acting on it. The thrust of the engines. Okay, the thrust of the engines, they push it forward. We have the drag or friction of the air around the plane that pushes the airplane backwards. There's its weight that pulls it down, and the lift on the wings that push it forward. So here we have on the diagram, we have your thrust, we have your lift, we have your weight, we have your drag. So let's look at the rest of the question. If we were to assume that the plane in the drawing is slowing down while flying horizontally, so it's getting ready to land, it's still flying horizontally, which is always a good thing when it comes to planes. Which of the 4 forces shown is greater than the other? Which are equal to the other? Explain your answers. So again, let's look at this right here. Okay, again, assume the plane is in the drawing is slowing down while flying horizontally. Which of the 4 forces shown is greater than the other? So maybe it's not even coming in for a landing, because then it would be getting lower. So let's just say, it's in the air and it's, going 300, 400 miles an hour, and they want to increase the speed, or they want to decrease the speed in this case. So which of the 4 forces shown is greater than the others if it's slowing down? Which are equal to the others? Explain your answers. So go ahead, write an answer down. Pause the video, fill in an answer, write it down. All right, so what did you have for an answer? Well, since the plane is flying horizontally, it's not moving vertically, which means that there are no unbalanced forces acting on it in the vertical direction. So the vertical forces that act on it, the lift and its weight, they must balance each other. This means that the lift must be equal to the weight. So which are equal to each other? Well, it's the lift and it's the weight. Now, since the plane is slowing down, it is subjected to an unbalanced force, backwards force. This means that the force acting backwards, the drag, must be greater than the force acting forward. So again, you could use your chart from part 1 to answer this. How do you get things to slow down? Well, just look at your chart. So you have to have an unbalanced backwards force acting on the plane. So how'd you do with this answer? Did you think to use your chart that you filled out in part 1 to help you answer this? Well, maybe you'll be able to use it for part 2. So if you look at your book, on the bottom of page 79, it starts. It says, the skydiver has opened her parachute and is slowly falling to the ground at a constant speed. What are the 2 forces that are, again, flip your page in, acting on the skydiver? Add them to the photograph. Also, what is the relationship between these 2 forces? Explain. Now, first of all, it says add them to the drawing. If you look at your drawing in your book has them already. There is lift, and then there's weight. Now, what do you think's the relationship between these? Do you think they're balanced or unbalanced? Look at your chart from part 1. What do you think? Now, let me ask you this. If you thought they were unbalanced, what's happening? Is the skydiver speeding up and going faster and faster and faster towards the ground? That would not be a good thing. Of course, if it was unbalanced the other way and the lift was greater than the weight, what's the skydiver going to do? It's going to keep slowing down to the point where they're not moving, and then they'll start moving upwards. That can't happen either. So the 2 forces acting on a skydiver are her weight and the upward force of the parachute. Since the skydiver is falling at a constant speed, the vertical force acting on her must balance each other. This means that the upward force of the parachute must be equal to her weight. It has to be balanced. If it's unbalanced, either this skydiver is going to be going faster and faster and faster, which is not a good thing, or they're going to be going slower and slower and slower until they stop, and then they're going to start moving upwards, which would be kind of strange as well if you're skydiving that you actually go upwards, which could happen if you have a really strong updraft. Now, let's look at the third one. So a runner is speeding as he nears the finish line. And I know you look at this picture and say, okay, if this kid's in track, why is he running in jeans? I don't know. It's just a picture that the book provided us with. So the runner is speeding as he nears the finish line. 4 different forces act on a runner, 2 vertical and 2 horizontal. What are these 4 forces? Add them to the drawing. Again, look at your drawing in your book. So it's kind of like, sweet, this is a bonus. They've already added the drawings. I don't have to do it. You're right. They already added it to it. So there's friction with the ground. Now, there's upward contact force with the ground, and there's drag and weight. Now, when we look at this friction, this type of friction wouldn't be dynamic friction, because when you put your foot on the ground, it's pushing up against it. Your foot's not sliding perpendicular to it unless you put both feet down and you were actually sliding. Here it's just pushing against the ground. So that would be a type of static friction. You have the upward contact force with the ground. You have your weight pulling you down. You have your drag, just like in an airplane. And so we have all the different types of forces here. Now, what are you doing? You're pushing your foot against it and you're pushing against it. Again, you're not sliding your foot. So this would actually be a type of static friction, because unless you push on the track and then your foot slides through, that wouldn't be good. If you were, speeding up and your feet kept sliding, it'd be like running on ice. You wouldn't be getting anywhere. So let's look at this picture as a whole. So we already have the 4 forces labeled. Also, what is the relationship between these forces? Explain. So go ahead, you got some space there. Go ahead and write in what you think the forces are. Well, here's your answer. And it's a long one. Now, don't write this whole thing down. You do have enough space, but paraphrase it. So the question was, what is the relationship between these forces? Well, the vertical forces are the runner's weight and the upward contact force between a runner and the ground. The horizontal forces are the friction between a runner's shoes and the ground pushing him forward, and the friction with the air pushing him backwards. So that's just explaining the things in a picture. So again, you don't have to have any of that. So since the runner is moving horizontally, not vertically, this means that there are no unbalanced forces acting on them in the vertical direction. And yes, I know runners tend to, bob up and down. But if you watch really good runners, if you watch the Olympics, their chest stays, in one spot. Their chin stays in one spot. Their bodies aren't bobbing up and down, because that's wasted energy. Really good runners don't do that. They don't move up and down, but they're moving horizontally. So this means that there's no unbalanced forces acting on them in a vertical direction. So the vertical contact force with the ground and his weight must balance each other. So what about the horizontal? Well, the runner is speeding up, so there must be an unbalanced force acting on him. So it has to be unbalanced. This comes from part 1 again. So the friction with the ground pushing him forward must be greater than the friction with the air right here, the drag pushing him backwards. Now, this is why a lot of times in track, especially if you watch, college and some high schools, but if you watch college, if you watch the Olympics, they have really tight clothing. Because just like in swimming, where they wear tight swimming suits so they don't have a lot of drag with the water, here, same with the air. They want to wear tight clothing so there's not a lot of drag between the air and their bodies. So in order to be moving forward, you must have unbalanced forces acting in the direction of the motion. So how did you do? Is that similar to what you were thinking? Hopefully. So let's review for a second. When an object speeds up, it is always subjected to an unbalanced force acting in the direction of the motion. When an object slows down, it is always subjected to an unbalanced force acting against the direction of motion. And when an object moves at a constant speed, it is not subjected to an unbalanced force. Forces must be balanced. Now, the last thing I'd like you to do is pull out your scientific principles. We're going to add a scientific principle today. So here it is. Actually, we're going to add a few of them. So the start and end of motion is always caused by forces. Things do not start on their own. Things do not stop on their own. They're always caused by forces. 10. Speeding up is caused by unbalanced forces acting in the direction of motion. So speeding up is caused by unbalanced forces acting in the direction of motion. And finally, 11. Slowing down is caused by unbalanced forces acting against the direction of motion. So again, make sure you have these 3 scientific principles in the scientific principles section of your book. And it should be stapled in the back. I think a lot of you stapled it in the back so you wouldn't lose it. It's that extra sheet. Again, as always, this is the end of the video. If you have any questions, make sure you ask. Thanks.